So we'll talk about the receiver diversity. Uh, and in the receiver diversity, you would have uh, more than one antenna placed at the receiver side so that you can improve the performance under fading. And we would call them number of branches. So we would have capital M number of branches so that we can improve the performance under fading. So the receiver, once you have some number of branches at the receiving end, or you have put multiple antennas at the receiver end, you have to combine the output of the received signals. And there are numerous ways in which you can combine the output at the receiving end, and we'll look at three of them. So the combining method, the first one is what is called the selection combining. So in the selection combining, as the name suggests, the output of the combiner would be the branch that has the maximum signal to noise ratio. So you would keep on looking for the branch that has the maximum signal to noise ratio, and the branch that has the maximum signal to noise ratio, that would be the output of your combiner. Um, the other another method that is used to combine different branches is called maximal ratio combining. And in maximal ratio combining, your combiner output is the weighted sum of the individual branches. That means you assign different gains to each of the capital M branches at the receiving end, and the goal of the maximal ratio combining is to combine these branches in such a way that you get the maximum signal to noise ratio at the combiner output. That is the goal of the maximal ratio combining, and you would soon find out that maximal ratio combining, or MRC to be short, is the optimal scheme that maximizes the signal to noise ratio at the combiner output. So of course that, because it is optimal, it would be the most complex of the schemes as well, because you need to have specific gains which are different for each of the branches. So a simple solution which is not which gives a very good which gives a very good performance, that would be a little suboptimal scheme compared to MRC. That would be much simpler. That is called equal gain combining. And in equal gain combining, what you do is you assign equal gain to all of the branches at the receiving end. So this receiver diversity combines the receiver output in a linear fashion. So we must look at what is the system model at the receiving end. How would you combine the output? So let's look at the system model for the combiner output. So that would explain lots of things. So, so this is the system model at the receiving end, and what you have is that there are capital M branches. So this is the generic diagram that can be used for all of the combiner method which we have mentioned. So you can see that you have this antenna one, this antenna two, this antenna M, and then on each of these antennas you are receiving a complex number, that is your received signal, that is R1 e to the power j theta 1 at the antenna 1, R2 e to the power j theta 2 at antenna 2, Rm is e to the power j theta m at antenna m, and all of these received signals have different phases and different amplitudes. So depending upon how the channel for this particular branch is, you will get a received signal, that is R1 e to the power j theta 1, and you may have a different, which would be, and the assumption would be that both of these received signals have undergone independent fading, and if the distance is good enough, that means that if this signal is in D-fade, this would not be in D-fade. Similarly, if this signal is in D-fade, this signal would not be in D-fade. So under this assumption, we would hope to improve the performance at the receiving end. And once you have the received signal, you would multiply the received signal with the gains. So alpha 1 would be the gain for the branch 1, alpha 2 would be the gain for branch 2, alpha m would be the gain for branch m, and then you would sum it, so you would combine it in a matter. For example, if you have equal gain combining, then all of these gains, alpha 1 all the way to alpha m, would be equal. If you have selection combining, then you would look for one of the branches. So this combiner output would only be one of the branches that has the maximum signal to noise ratio. And then, so this would you would do in the hope that your gamma sigma, which is your signal to noise ratio at the combiner output, is greater than uh, your branch signal to noise ratio is given as gamma I. Uh, so that is your system model at the receiving end. And one important thing is that your receive signal has different phases. So what you need to do is we need to have a mechanism so you to take care of the different phases of the receive signal. So for example, so if I draw the polar coordinates for a complex number, so this is the unit circle, for example, and suppose that your receive signal at the antenna 1 is this complex number, which is R1 e to the power j theta 1, and the receive signal at antenna 2 is this R2 e to the power j theta 2. Now, if all of these signals would combine in a vector form, that means uh, this would be equivalent to the fading scenarios. That means if all of these signals are not co-phased and they have different phases, and that phase is uniformly distributed from 0 to 2 pi, then all of these branches would have no use. They would not bring any gain because all of these would be what you get at the combiner output uh, would be the vector sum of all these branches. But that is what you need to do by multiplying with these gains alpha 1, alpha 2, alpha n. Remember, these would also be complex numbers. So the important thing is that if, for example, alpha I is the gain of your ith branch, then angle of this alpha I must be equal to minus theta I. That would means that would co-phase that. For example, you have two branches here, r1 e to the power j theta 1. If r1 e to the power j theta 1 is multiplied with a e to the power minus j theta 1, so this would cancel out this phase, and this would bring this complex number onto this x-axis here, because these phases would combine together in a manner so that you have zero phase here. Similarly, if this r2 e to the power j theta 2 is multiplied with a2 e to the power minus j theta 2, that means all of this phase would be nullified again, and you would come here, and this would be your uh, so this complex number would bring here, that would be R2A2. That would be the magnitude of this branch. So that mechanism is called co-phasing. And without co-phasing, your uh, receiver output would still be undergoing fading. This co-phasing is important. That's why you multiply with these gains so that these are co-phase signals. But this co-phasing sometimes would require what is called the coherent detection, because you have to have a mechanism to lock the phase of the incoming signal, and that requires coherent detection. So this co-phasing requires coherent detection, and with this co-phasing, you would get an improved performance. Otherwise, as I said, that would it would not bring any advantage. So now let's look at what would happen uh, to this receiver structure. For example, if you have no fading, right? In the absence of fading, of fading, if you have put these capital M antennas at the receiving end, what would happen then? So let's assume that all of these branches have this receive signal Ri, that is equal to root of Es, and suppose that all of these branches have equal or identically distributed, not equal, identically distributed noise. So this would mean that the received signal to noise ratio gamma I for each of these branches would be Ri squared over your noise power. That would be equals to, suppose n naught by 2 is the noise variance, times 2b would give you the total noise power, and Ri squared, which would be equals to Es divided by Ts, would give you uh, the signal power. So that would be equals to Es over this 2 cancel with this 2, b times Ts times n naught. And if we assume that b times Ts, that means that your bandwidth and simple interval product is equal to 1. So this branch SNR is Es over n naught. So let me explain what I have done is, in the absence of fading, suppose we have no fading at all. So what would happen? So suppose we have Ri is equals to root Es, and for each of the branches here you have the same signal that you are receiving here, and what would be the signal to noise ratio on each of the branches, that we have said that would be equal to Es over Ts. That would be your received signal power divided by n naught by 2 times 2b, or n naught b would be your noise power. So Es over n naught under these assumptions would be your branch SNR for each of these branches. So now under these scenarios, what would be your received signal here? So your received signal here would be equals to summation I equals to 1 to capital M AI or alpha I times your Ri, which is your received signal. And here I am assuming this Ri is a complex number, and plus you would have these noises, and I is equal to 1 to n, and then your noise would be added together. So if and if of course it would get multiplied with AI as well. So your noise would also get multiplied uh, with the gain that you are multiplying uh, for each of the branches. So remember, if each of these branches have n naught by 2 as a noise variance, then the noise variance for at the combiner output. So let me call it n total. So your n total would be equals to summation I equals 1 to n uh, ai squared or alpha I squared times n naught by 2. So that would be your noise variance, right, for at the combiner output. And now if you want to talk about what is the signal to noise ratio at the combiner output, let me call it gamma sigma. So gamma sigma would be the signal to noise ratio at the combiner output. And remember, we are not assuming here. So let me show it again. Remember, we are not assuming any fading for the moment. We just want to see that whether these M branches give you a gain in terms of the signal to noise ratio when we have no fading at all. That would give us an idea of whether or not these M branches is giving you some help or not. So this gamma sigma would be equals to E S total over N naught. So that would be equals to summation I equals to 1 to capital M AI times Ri whole squared divided by N total. Where remember, this would be n total by 2. Remember, this would be your noise variance at the combiner output, and n total, because again this is analogous to es over n naught, where n naught is your n naught n total by 2 is your power spectral density of the noise. So this n naught by 2 is the noise variance or the power spectral density if it is a white Gaussian noise. And your gamma sigma at the combiner output would be this sum, which is the signal part. The signal part is summation I equals to 1 to capital M AI RI, and square of that would give you ES total divided by n total, that would give you the gamma sigma. And now let's see whether or not we get some gain here. So to compute that, let's assume that your AI is equals to your Ri over root n naught, where Ri is also root Es for each of the branches here. So this would mean that your gamma sigma is equals to um, summation I equals 1 to capital M. AI is Ri over root n naught times Ri whole squared divided by n total. So let's bring it down here. So this means that your gamma sigma is equals to summation I equals 1 to capital M Ri squared whole squared, and this root n naught squared would be n naught, and that you can bring out of this summation, because this is a constant and it's not a function of I, divided by n total, which is given by here. So this 2 times n total by 2 would give you n total, and that would be equals to summation I equals 1 to capital N AI squared times n naught, and where AI is Ri over root n naught. So that would be equals to Ri squared over n naught times n naught. That cancels out. So what you have is summation I equals 1 to m times Ri squared whole squared, and in the denominator you have summation I equals 1 to m Ri squared. So this entire thing would cancel out this square, and what you are left with is 1 over n naught summation I equals 1 to capital M Ri squared, which is nothing but Es, and hence your gamma sigma is nothing but summation I equals 1 to capital M Es over n naught, which is m times your uh, which is m times Es over n naught, or which is nothing but m times your individual branch SNR. In other words, even in the absence of fading, what we have proved is that with this structure where you have capital M number of antennas uh, in your received signal model, you can have a received signal power that is much greater than the individual signal to noise ratio. Now that was in the absence of fading. What happens in the presence of fading? So we'll talk about that. So this, by the way, is also called what is called array gain. So that you can also call array gain. So you had an array of antennas at the receiving end that is providing you a gain in terms of signal to noise ratio. That gain, array gain, is nothing but your gamma sigma bar, which is your received signal to noise ratio at the combiner output on average, divided by gamma bar, which is your signal to noise ratio of each of the branches. So this is average SNR of each of the branches, and this is your average SNR at the combiner output. So this array gain is the gain in the signal to noise ratio that you get on average. So that is the array gain. So now So as we said that even in the absence of fading, you get some array gain here. That is proportional to the number of branches you had in the receiver array. And now, what is the performance metric under fading? That is important. So under fading, the performance metrics that you would have are the same which we talked about in the last chapter. And one of the performance metrics is what is called the outage probability. And outage probability is nothing but the probability that your gamma sigma now, because you would talk about gamma sigma, which is your signal to noise ratio at the combiner output, is less than some threshold gamma naught. So that would be your outage probability. And similarly, you would have this average symbol error probability as a performance metric, and that would be equals to integral from 0 to infinity Ps of gamma, which is your symbol error probability under AWGN, times P gamma sigma of gamma d gamma, where P gamma sigma of gamma is the PDF of the fading distribution at the combiner output. So that is how you would now measure the average symbol error probability and whether or not you get an improvement in uh, the average symbol error probability or outage probability after after you have combined your received signals in this manner. So what typically so there are two gains that you typically talk about. One is the array gain that you get in the average signal to noise ratio, and another gain which you would talk about a lot is what is called a diversity gain. So the diversity gain is related to the what is how much improvement do you get in the curve of your symbol error probability. So typically what you would have is that your average symbol error probability after combining would be some constant C1 uh, times your gamma sigma bar to the power minus m. So, so this to the power minus m means that you would have a diversity order of m. So this would be a diversity. This means you have the order of m. So that m is related to the slope change in slope of your average symbol error probability. So if you take the derivative of this m would come here, would get multiplied with the gamma sigma. So if this is your equation, so you would have a diversity order of capital M, and that is what you would be looking for. That what diversity order you get with the combiner at the combiner output if you combine it with different techniques. If you recall that your average bit error probability under fading, we looked at the average bit error probability of BPSK modulation under relay fading, and if you recall, that was 1 over 4. That was approximately equal to 1 over 4 times gamma B bar. And you can see that this is equals to 1 over 4 times gamma b bar to the power minus 1. So you have a diversity order of 1 here, uh, which is totally to, which should be the case because you have only one antenna at this point in time. So once you have more number of antennas, so you would get a better diversity order, and this one would be increased by some number greater than one. So that is the gain or the performance metric that you would be looking for under fading. So next we will look at the performance with selection combining.